Alright, so we're going to start the next chapter today, acids and bases. We've already talked about them and used them quite a bit, but we haven't just talked about their properties yet. So, what is the most common acid that we've used in lab several times? Hydrochloric acid. So the last lab, excuse me, we used 12 molar hydrochloric acid, right? And I told you not to get it on you, correct? And nobody did, hopefully. So just to kind of show you what it does to you, here's an egg. Okay. So here is the bottle from the lab, the 12 molar hydrochloric acid. So if we put the acid on the egg, you see it?
No.
And so you don't want that happening to your hand. Okay? So we're not going to get these on us. Okay? Silver nitrate stains, hydrochloric acid burns. So I'd rather be stained than burned. So before we get started talking about acids and bases, let's first review naming them. So when we first started naming compounds back in December, we said there were three major groups that we named: ionic, covalent, and acids. Okay? So acids are covalent compounds, but they get named with special rules. How do I recognize if I have an acid? Starts with an H. Okay? So there are two categories of acids: binary and oxyacids. So binary means what? Two. So we said that acids start with an H. So if they start with an H and have two pieces, it's just an H plus one other thing, right? So the rules for naming binary acids, you hopefully remember, is hydro plus whatever the base of the other element is, and then the ending IC in the word acid. Okay? So HCl, is it a binary acid? Yes. So what is the name of HCl? Hydrochloric acid. Are any of the others 1 through 6 binary acids? 5. So what is the name for 5? Hydrofluoric acid. Okay, so those are easy. Then the oxyacids contain what? An oxygen. They're typically hydrogen plus a polyatomic ion. Naming them depends on you knowing the name of the polyatomic ion. So we name it based on the polyatomic ion that ends in ATE. So I'll write some examples. So I have HClO3, HClO4, HClO2, and HClO. So what is the name of ClO3 negative 1? Chlorate. What does chlorate end with? ATE. So we use this rule. Add the IC ending. So this is chloric acid. That's the most commonly missed one. Because we're so familiar with HCl, we see chloric acid, not HCl. What is HCl? Hydrochloric acid. Okay. So then, if I add one oxygen, so up one, I have per blank ic acid. So perchloric acid. Does this all seem familiar, hopefully? Okay. So then I go back to the ATE polyatomic ion, subtract one oxygen, I have the ITE polyatomic ion. That ends in OUS. So then I have chlorous acid. Then if I take away one more oxygen, I have the hypo prefix, so it's hypochlorous acid. Okay. Questions about that? So looking at writing the formulas, what can I go ahead and write to start every single one of these? An H. Then for hydrobromic, what is the other piece of hydrobromic acid? Br. How do I determine how many hydrogens I need? The charge. So HBr needs how many hydrogens? 1. Because what's the charge of bromine? -1. Okay. So go ahead and take 2 minutes and finish 1 through 6 and 1 through 8 really quickly. I'll write them up here so you can check your work. So there's the answers. When you're done, look up and check. Number 3, you can also write HCH3COO if you memorize acetate like that. Numbers 2 and 7 need 2 hydrogens. Number 8 needs 3 hydrogens. So this should be all review. You had a test on this already. Any issues? Good. So you should be able to write the formula or name any acid, but I'm going to write some at the top of the paper that you need to know immediately, the ones we're going to use most commonly. That would be HCl, which is, what is it? Hydrochloric acid. H2SO4, which is sulfuric acid. HNO3, which is nitric acid. And then HC2H3O2, which is acetic acid. Yeah. So those are the ones I want you to know immediately with no thought. So if I say nitric acid, you should know HNO3 immediately. Okay? And those are the 4 we use most commonly. So the rules for naming acids are somewhat complicated. Naming bases are very easy. So bases typically follow the form metal OH. Okay, so what is OH? Hydroxide. So a metal plus a hydroxide is an ionic or covalent? It's ionic. Metal plus a polyatomic ion is ionic. So do I use prefixes or anything for ionic compounds? No, so I just name them. Okay. So what is the name of NaOH? It's what? Sodium hydroxide. BaOH2. Barium hydroxide. CuOH2. No. Copper 2 hydroxide. So iron 2 hydroxides, FeOH2. Calcium hydroxide is CaOH2. And then nickel, I don't know why it's abbreviated. It should be NiOH2. So, is that anything new at all right there? No, other than the fact we call a metal hydroxide a base. That's the only thing new. So, now we can name and write the formula for our acids and bases. You already could do that, let's review. So if you look below, there are some general properties of acids and bases typed out. Okay? So we'll introduce them now, then we'll spend more time talking about them in the coming days. So the first property of an acid is they taste sour. Where's the common place you encounter something sour that you eat? What fruit? Lemons. Lemons contain citric acid. That's why they're sour. Okay? What else do you have in your kitchen that tastes sour?
Lime.
Well, same family.
Lunges.
What do you do with a cucumber?
Pickles.
Make pickles. Okay? So vinegar is acetic acid. And so acids typically have sour taste. That's kind of a fun fact, FYI. We don't taste things to determine if they're acids or not. So the indicator section we'll come back to. We'll talk about what indicators are in a minute. Then it says acids have a pH lower than 7. So you learned a couple years ago the pH scale typically goes from what to what? 1 to 14 is what you typically learn. You can go negative, you can go above 14, but for this class we typically stay between 1 and 14. So 7 would be, but what's the word for it? Neutral. Okay, so 7 is neutral. Below 7 is acidic. Above 7 is basic. We'll talk about that more in a minute. The next is what the definition of an acid is. So acids are proton donors. There's multiple definitions. That's the first we'll learn there. So if you're a donor, what do? Give something. Okay. So look at the periodic table. How many protons does hydrogen have? 1. It has a molar mass of 1.01. So do most hydrogens contain a neutron? No. How many electrons does hydrogen have? 1. So if hydrogen is 1 proton plus 1 electron, if it loses the electron, what's left? Proton. So H plus is just what? Just proton. So a hydrogen ion is just a proton. So H plus and proton can be used interchangeably. Those are the exact same thing. Once a hydrogen loses an electron, it's just a proton. That's all that's left. Okay. So what do acids do with these protons? They donate, give them away. Okay. We said that acids have to start with what? Hydrogen. So does it make sense they would give away a hydrogen? They all have to have it, so we recognize them. Okay. Then we say that acids react with metals, they react with carbonates, they react with bases. We'll spend more time on that. And the last one, we already learned when an acid dissolves in water, it does what? It ionizes, which means it, what is ionization? What does it really do? It separates, breaks apart. So it breaks apart and forms ions. Okay. So then the general properties of bases are almost all the exact opposite. So bases tend to taste bitter. We'll come back to the indicators. pH higher than 7. So bases accept protons. So they take protons. So if acids like to donate and bases like to accept, does it make sense that acids and bases would react together pretty well? Yeah. So it says they feel slippery. That's because bases react with oil to make soaps, or fats to make soaps. What does your skin constantly secrete? Oils. So bases react with oil in your skin to make a soap-like molecule, so they feel slippery. Bases react with acids, and then last, bases dissociate. So we said bases are typically metal hydroxides. Are metal hydroxides ionic or covalent? Ionic. What do ionic compounds do when they dissolve? They dissociate. Okay. So let's look back at the indicator category. So for indicators, it says acids turn blue, litmus paper red, and neutral litmus paper red. So litmus paper is just special paper that you can buy that's used to test for acids and bases. So this is red and blue, or you can buy the neutral kind that's just white. Okay? So acids turn the paper red, bases turn the paper blue. So if I dip the red paper in a base, it would turn blue. If I dip the blue paper in an acid, it turns red. If I dip the white paper in an acid, it turns red. Base turns blue. So just remember, bases turn litmus blue. So another common indicator that we use to indicate if it's an acid or a base is that P word. What is the P word? I heard it. Phenolphthalein. That's how it's pronounced. Everybody say it. Phenolphthalein. Phenolphthalein. Okay. So phenolphthalein is just a clear, okay, solution that we have. And what color does it turn when it's in an acid? Or it stays clear. It's already clear. What about in a base? So again, in a base it turns pink. So we can use this to determine if we have an acid or a base. So in one of these cups I'll pour an acid, and one I pour a base, and then one I'll pour some water. I guess I could put it on the camera. I hadn't spilled this all day. I'm trying to keep my streak going. Alright, can y'all see this on the camera? Sort of. Good enough, right? So, as I add this, tell me what it is. So, do anything happen? No. So is it the base? No. So either the acid or the water, right? So either acid or water, right? I didn't pick it. I picked up the wrong bottle. Let's try that again. Pick up the right bottle this time. Take two. I guess I should read the labels. Round two. Now, what is that? Base. So if you look at the phenolphthalein bottle, it is clear. The base was clear. You add it, it turns a nice pink color. Okay. So can we use this to differentiate between acids and bases? Yes. But can I use this to determine the exact pH? No. For that, we have what we call universal indicators. So universal indicators just bottles of solution that come with papers that give us an actual range of pHs. So this, when I add it, if it's pH 1, turns that color, pH 2 turns that color. So I can use this to figure out a more precise pH. So let me dump out the pink. Alright. I've got acid in one already. And I'll put base back, I hope so. Put base in one. So the base is just sodium hydroxide. Then I'll put my water in one. So my water should be close to what? 7. So can y'all see those? No. So I'll take this, my universal indicator. So now, can I use that to determine more exact or more accurately what my pH is? Yeah. So the pH of my acid's close to 1, 2, somewhere in there. My water is pretty close to, we can say 5. Okay. Then my base is, can we say for sure it's 7 though? What's the highest this goes? 7. That's kind of the issue with this. It only has a limited range there. So you will probably never ever do that because now those solutions are kind of useless, right? They're colored forever now. What you typically do, you already have done in the lab, when you took the little piece of pH paper and put the drops on it and recorded the color, That is just a strip of paper that has been soaked in this and dried. So if I soak paper in this stuff, I can just dip the paper in the solution and match the color up. That way I don't waste the solutions there. Okay? So we'll use several different indicators for labs this year to figure out the pH. And we also will use a pH probe. So there is an instrument that you stick in a solution and it digitally reads the pH and tells it to you. Okay? Phenolphthalein is not toxic, or it's not corrosive, it won't hurt your skin. It is, however, a former laxative. They sell it as a laxative. Okay? This is a very pure, concentrated version of it. Okay? So do you want to get it on your hands and get your hands near your mouth? No. It is very good at what it does. Okay? So you don't want it inside of you. So hydrochloric acid will do what to you? Burn you. Phenolphthalein will do other things to you. So you don't want it inside you. It'll cleanse you. Okay? So now, let's turn over to the next page and look at some other things. And so we typically classify acids and bases as one of two things, either strong or weak. So that doesn't mean strong is dangerous and weak is not. That's the common misconception. When you hear a strong acid, you think probably don't mess with it, right? If you hear weak acid, you probably think, well, it's probably okay to work with. So there's really no correlation there. We'll kind of discuss why in a minute. The definition of a strong acid is just that it ionizes 100%. Okay? So an example of a strong acid is hydrochloric acid. So if I take HCl, liquid, plus H2O, liquid, what does an acid do when you add it to water? It ionizes. So if this is strong, how much does it ionize? 100%. So if I put 75 HCl's in water, how many of those are going to ionize? 75. All 75. Okay. This is useful because if I have 1 mole of HCl, how many moles of protons does it make? 1. Okay, so 1 mole ionizes completely. So 1 mole makes 1 mole of protons. Okay? So now, weak acids ionize less than 100%. So if I have a weak acid, like acetic acid, we see this. Kind of ran the room there. So now, if I put 75 acetic acids in water, how many of those 75 are going to break apart? Less than 75. So we know exactly how many. Now we'll calculate that later. Okay, but for now we don't. We just know it's less than 75. So we have an equilibrium established. Okay. So we'll use that equilibrium constant we can calculate to do calculations in the future. Okay. Would the HCl dissociation have an equilibrium constant? Is it a reversible reaction? So according to this, it's not. It really kind of is, but for this, we'll say it's just a forward reaction with no reverse reaction. Okay. So now you can probably imagine these calculations could be more complicated. HCl, we know 1 HCl makes 1 H, 1 Cl minus. But acetic acid, we don't know yet. We have to calculate first how much it ionizes, then we can calculate how much that reacts. Okay, so then acids ionize. What do bases do in water? Dissociate. So the strong weak rule is the same. Strong bases dissociate 100%. Weak bases do not. What determines how much something dissociates? Solubility. So if something is completely soluble, will it dissolve and dissociate? Yeah. If it's not soluble, it will not completely dissociate. Okay. So we focus more on strong and weak acids, and we don't really worry about strong and weak bases because almost all the bases that we use are strong. We use sodium hydroxide, potassium hydroxide. Typically, we only use strong bases. So now let's think about if I have 0.000. Okay. So that's saying there are 0.00001 moles per 1 liter, right? So is that concentrated or dilute? Very dilute, okay? You could swim in that. Would not hurt you, okay? Is hydrochloric acid a strong acid? Yes. But is that, what I wrote down, going to be dangerous, that solution? No, you can drink it. It's not going to hurt you. But then, if I have this, what is HC2H3O2? Well, it's acetic acid, which is vinegar. It's a weak acid, okay? So, do you drink acetic acid? If you drink pickle juice, you do, okay? So you can, but 12 molar acetic acid will burn your skin. Is acetic acid weak? Yes. But in this situation, the 12 molar tells me it is also what? Not strong concentrated, okay? So when we think about how corrosive it is or how dangerous it is, we consider concentration, okay, not strong versus weak. Strong versus weak tells me how much it ionizes, not how dangerous it is to have around me or what it's going to react with, okay? Questions about that? So let's look at a few of the reactions that acids do. So this reaction right here is what type of reaction? Single replacement. Have we done those already?
Yes.
Yeah. Okay. So metal reacts with acid to make zinc chloride plus H2. Will metals reacting with acids always produce hydrogen gas? The hydrogen is being replaced, that makes H2 gas and it bubbles off. But will all metals react with acids? No. How do I figure out which ones will? Not the activity series. Figure out if it's reactive enough to replace the hydrogen. Is that anything new? No. Okay. So this is a really long time ago. We learned that acids react with carbonates to make water, H2O, plus CO2. Plus, what else have I not used up in this reaction? Calcium, sulfate. And so they make water, carbon dioxide, and then whatever's left over. That's not a new reaction. You learned that one. It's been a while though. Then the last one is the most important one. What type of reaction is this? It's double replacement, right? So do I just switch the H and Na? Yeah. But it's a special double replacement called a neutralization reaction. So that's what we call reactions between acids and bases. They are neutralization reactions. And they always produce salt and water. Does salt refer to sodium chloride? No, sodium chloride is a salt, okay, but salts are what? Ionic compounds, okay. By definition, a salt is the product of a neutralization reaction, okay. So look at this. What is that? Acid, base, neither. Acid, what is that? Base. So could I just follow the old double replacement rules and switch and get the right answer? Yeah. Or I could recognize you get salt plus water. So salt plus water. Let's look at another one. Let's look at HCl, AQ plus NaOH. AQ. So is that a neutralization reaction? Do I have an acid plus a base? Yeah. So what's my first product that's the easy one to write? H2O. I know that one. And what's my other product? NaCl. What phase symbol does it get?
Aqueous.
AQ. It's dissolved in water. So in theory, if you took 12 molar hydrochloric acid, which will burn you, 12 molar sodium hydroxide, which would irritate your skin, and mixed it together, could you safely drink it? In theory, yeah, you can make salt water. Okay. And this is a coincidence that it's sodium chloride. Sodium chloride is a salt, but it's not the only salt. We don't always make sodium chloride plus water. Is it balanced? Yeah, this is balanced already. Okay. Questions? We got off topic first, Bree, that's as far as we got, so we can stop there for today. Or do y'all want to keep going? No, okay. Yeah. Yeah, hey, good question before I stop. So double replacement, we always look to see if there was a solid or a liquid product. So if water is always a product, water is always going to be a liquid, so the reaction always happens. Okay, good question.